All right, this is section 12.4, the cross product. This is going to be the second of our vector multiplications. So the first thing we're going to do is we're going to cross all of this off. There is no bookwork, just the WebAssign. It's from a much older time when I was doing this differently. Okay, so our outcomes, we're going to define the cross product of vectors and then discuss the properties and applications of what the cross product does and what it means. So while the dot product of two vectors yielded a scalar, and we saw that in the previous section, the cross product of two vectors is going to yield a vector. That is definitely a typo. That should say will yield a vector, not with yield a vector. Okay. Definition. If vector A is defined to be A1, A2, A3, and vector B is defined to be B1, B2, B3, then the cross product of A and B is given by A, with the little X in between, that's your cross product symbol, A cross B, is A2, B3 minus A3, B2, comma, A3, B1 minus A1, B3, comma, A1, B2 minus A2, B1. Not incredibly easy to memorize something like that. So let's come up with a way so that we don't have to memorize all those little sub numbers and everything on the components. So there's another way to write this using I, J, and K. While the above formula looks a bit cumbersome and it is difficult to memorize, we're going to use the idea of a determinant to find the cross product. Much, much easier to do. So the first thing is, let's discuss what a determinant is and how to find its value. So a determinant, first of all, is going to be made from a matrix. So we're going to create a two-dimensional matrix and just show the idea of what we're doing. So let's find the determinant of, let's do the matrix 1, 2, 3, 4. So we'll say find the determinant. Determinant. Okay, not to be confused with the discriminant. The discriminant is what's underneath of the square root in the quadratic formula. This is different. This is a determinant. So how do we find a determinant? So a determinant is actually going to be, it is the product of the main diagonal. So what's the main diagonal? Well, the main diagonal starts from the upper left of the matrix to the lower right. So this right here is your main diagonal. So it is the product of that main diagonal minus the product of the minor diagonal or off diagonal. I'm not sure exactly what the word is for that one actually. And this is the minor. So it's the product of the major minus the product of the minor, or the main diagonal and the off diagonal, however you remember it. The main diagonal goes from upper left to lower right. The other diagonal goes from the lower left to the upper right. So it's always going to be that way. So the easiest way just to think about it is always start like you read a book, upper left corner. So that's where you're going to start. So the product is going to simply be 1 times 4 minus the product of the other diagonal, 3 times 2. So here we would get 4 minus 6, or a determinant value of -2. Okay, that doesn't really hold a lot of meaning for us yet. It doesn't actually tell us why we're doing any of this stuff, but that's just how you find a determinant of a 2x2 matrix. So let's write this out in words. It was the product of the main diagonal minus the product of, let's just call it the minor diagonal. or the off diagonal, however you want to say it, but it's not the main diagonal. So in general, we can find the product, we can find the determinant for a 2 by 2 matrix if this is A1, A2, B1, B2, or basically think of those as the components of a two-dimensional vectors. A1, A2 would be the components of a two-dimensional vector. B1, B2 would be the components of a two-dimensional vector. It would be the product of the main diagonal, A1, B2, minus the product of the off diagonal, and I'm just going to write it alphanumeric first, so it's A2, B1, so alphabetical. That's it. That's all there is to finding the determinant of a 2 by 2 matrix. Of course, that's only if we're given vectors in 2 dimensions. If we apply that idea now to a 3-dimensional matrix, and we include the I, J, and K vector, or basically remember that those are the unit vectors in the direction of X, Y, and Z, so we can just say that I, J, and K are the unit vectors, we can more easily find a cross product. So it's a crucial idea in the rest of Calc 3. It's also going to apply to linear algebra and probably will apply to some of the sciences that you may take in the future as well. So let's go ahead and show how we find the determinant of a 3 by 3 matrix now. So now we have a 3 by 3 matrix. So let's say that, again, we have 2 vectors. The first one is A1, A2, A3, because now they're 3-dimensional. And then the second vector is B1, B2, B3. Well, in order to actually do the determinant, first of all, a determinant can only be done if the matrix is a square matrix, meaning it's got to be a 2 by 2, a 3 by 3, a 4 by 4, a 5 by 5. You cannot have some other dimensional matrix, which again is more of a linear algebra topic. We won't be dealing with that anyway, but you cannot do that. So what we need to do is we need to create the 3-dimensional matrix by including, that should be an I, not a J, I, J, K. All right, so here's the idea, and I'm going to try not to get too linear algebra on all of this because we don't really need to understand all the ins and outs of how all this works and all the specific ways of saying things. We just need to kind of be able to do it at this point. I don't usually like saying that, but it's a whole nother topic. Okay, in order to do this, we need to create what are called co-matrices. And to do that, we're going to use what's called the process of cofactors. Again, not something you're probably going to hear me say too often, but that is the general idea. So the idea is I need to create a co-matrix which is multiplied by I. So I, remember, is just the unit vector in the direction of X. So what we're going to do is we're going to use I as the first cofactor. So what I do is I actually look at the I, and I'm going to eliminate the I row and the I column. And what that leaves us with is that A2, A3, B2, and B3, which is not highlighted. So I'm going to actually get rid of that, but you could see what I was doing there. So that's going to leave us with I times the matrix that was left over when I eliminated the I and the J, the I row and column. That's going to leave us with A2, A3, B2, B3. Okay, this is actually the process that we're going to use for all of them. We need to do exactly the same thing with the J. So if I were to eliminate the J row, which is that one, and the J column, which is that one, it leaves us with A1, A3, B1, B3. Don't change the order. It's got to stay in the same order. So I'm going to get rid of those lines real quick. So that's going to leave us with J times, again, A1, A3, B1, B3. And then the last one, as you probably guessed, is the K. So if I were to eliminate the K row and the K column, that's going to leave us with A1, A2, B1, B2. So over here, we're going to write K and then times A1, A2, B1, B2. Now here's a very, very important piece. In general, in a matrix, when you're doing a determinant, there's a positive and negative flow chart with these things where the upper left piece or the very first component where the I is positive. And then if you were to go to the right, it switches the sign. It's going to go positive, negative, positive. So for example, this would be a positive, negative, positive along that row. It also does the same thing as you go down as you go down the left-hand side. So it's positive here, negative there, positive there. It doesn't mean the values will be negative. It just means that they're going to change their sign, very much like in ABBC when we were doing integration by parts, and every other one when you did the tabular form, change the sign. If you remember when we did that stuff, it's the same idea. So it's not really telling you that the value will be negative. It's just telling you to change the sign. So the first one is positive. The second one, however, we need to make negative. And then the last one, we're going to keep the sign. So we're changing the sign of J, always going to do that. All right, so now let's go ahead and actually finish this off. So now what we have is we have I doing the 2 by 2 determinant that's multiplied times the I is A2, B3 minus A3, B2. Main diagonal, off diagonal. Minus J, times A1, B3, main diagonal, minus A3, B1. And then the last one is K times A1, B2, main diagonal, minus the minor diagonal, A2, B1. And that's the formula that I gave you guys on the first page. Again, very cumbersome formula, but you don't really have to memorize it. You just kind of have to know how to do this. It's not going to be that difficult if you remember how to do it. So it's always going to be a main diagonal minus an off diagonal with 2 by 2 matrices. With a 3 by 3, you have to break them down. We can get this thing higher into 4 by 4, 5 by 5, and it just takes it's a long, tedious process to keep breaking everything down. We will not deal with that. We're stopping at 3. So this is as far as it goes for us. All right, so let's actually do an example, and hopefully this will make sense when you see it with numbers. We'll want to do the cross product of A, which is 214, and B, which is 163. So to do the cross product, we'll just set up our determinant, a 3 by 3 determinant, always going to have I, J, K across the top. And then I'm going to do the cross product of 214, 163. All right, so let's go ahead and do I. So it'll be I times the 2 by 2 determinant that's left over when you eliminate the I row and the I column. Well, that should be 1, 4, 6, 3. Remember, we changed the sign of J, and then we do what's left over when we eliminate the J row and column, which is going to be 2, 4, 1, 3. Whoops. 2, 4, 1, 3. I don't know what I was doing out there. Okay, and then the last one is plus K. What we get when we eliminate the K row and column will be 2, 1, 1, 6. Okay, and now we can actually figure this thing out. So we're going to get, let's see, I will be multiplied by 3 minus 24. J is going to get multiplied by 6 minus 4. And K is going to get multiplied by 12 minus 1. So we should get negative 21I. We're going to get minus 2J. And then we're going to get plus 11K. So ultimately, and you can write this in both ways, but the easier way to write it is in vector notation. It's negative 21, negative 2, 11. This is the cross product of 214 and 163. It gives you the vector negative 21, negative 2, 11. Okay, so let's try one more. Let's do the cross product of I, J, K, 3, 3, negative 2, 5, 1, 0. I'll move through this one just a little bit quicker. So eliminating the I row and column is going to give us 3, negative 2, 1, 0. Eliminating the J row and column, don't forget to subtract the J, is going to be 3, negative 2, 5, 0. And then the K row and column is going to leave us with 3, 3, 5, 1. All right, so let's finish I. So that's going to be 0 minus negative 2. So that's really going to give me 2I. This next one is going to give me 0 minus negative 10, which is positive 10, but don't forget we're subtracting, so it's still minus 10J. That's going to be the most tricky part when you've got like 3 different negative things going on there. And then the last one is going to be 3 minus 15, so we get minus 12K. So our vector is 2, negative 10, negative 12. And that's the cross product of A and B. All right, let's go ahead and talk about some of the properties and kind of what it means for us. And then we'll come back and actually do the applications in a second video. So the properties. If I take A and cross it with itself, and you can actually try this, take any vector and do the cross product of it with itself, you actually end up with the 0 vector, also written like this. That is not O vector, that is the 0 vector. That's why we don't use O as a variable. Make that an actual 0, that's better. So any time you cross a vector with itself, you will get the 0 vector. Okay, hopefully all that will be explained when we actually get into the why of all this. If we take A cross B, it is not the same as B cross A. As a matter of fact, it will give you exactly the opposite sign. So switching the order of the vectors that you cross, so if you were supposed to cross A and B, A cross B, but you accidentally wrote the B vector in the second row instead of the A vector, it will give you exactly the opposite answer. So all the signs will be changed. So what that really tells us is that cross products are not commutative. We cannot change the order of the cross product and get the same thing, at least not all the time. There are going to be obviously some examples where that works, but most of the time, no. And then if I were to take A cross B and dot it with A, and I get 0. And then if I were to take A cross B and I dot it with B, I would also get 0. Now, if you remember from when we did the dot product, if we take two things and we dot them and we get 0, that means that those two things that we dotted together are perpendicular or orthogonal to each other. So what that actually tells us for both of these examples, if I take A cross B, it is going to be perpendicular to A. And if I were to take A cross B, it is also perpendicular to B. Now let's actually think about what that means. I just told you that if I take two vectors and cross them, those vectors are perpendicular to both A and B. So they're perpendicular to both of the vectors that I just crossed. Try wrapping your head around that one for a second. It's not easy to see unless you're actually like already seeing this visually in 3 dimensions. So the cross product of two vectors is perpendicular to both vectors. So how can we do that? How can that be? How can a vector be perpendicular when I cross it to both of the vectors? Well, again, you have to think three-dimensionally. So in 3D, let's just sketch ourselves our x, y, and z real quick. Think about this. If I was to take the cross product of the x-axis and the y-axis, well, the x-axis and the y-axis are currently already perpendicular to each other, but that doesn't matter. What matters is if I were to take the cross product of the x-axis and the y-axis, I would actually get the z-axis. And the z-axis is a vector which is perpendicular to both the x and the y. As you can see, I'll kind of try and sketch this in, perpendicular to x, also perpendicular to y. So by crossing two vectors, you actually get a third vector which is perpendicular to both. So again, you kind of have to think of it three-dimensionally. The easiest way to think about this is think about the corner of a room. Okay, again, just like I said with when we're trying to figure out the x and y axis, including the z axis now, if we think about the corner of a room, you've got two pieces at the bottom on the floor that come together. If you were to cross those two, you would get the vertical one, the z-axis. And this can be said for anything. So let me see if I can just kind of sketch this. If I were to take any two vectors in space and do that, if I were to cross these things, now these two things are obviously not orthogonal to each other, I would get a third vector by doing the cross product, which is perpendicular to both of them. That is going to be what happens when you do the cross product. Okay, we're going to come back in a second video and do all of our applications. Sorry about all this. I'm actually trying to find, there we go, there it is. Trying to find my recorder. And that'll be it for the day after we do the second video.